Okay, in this video, we're going to figure out how to find local extrema. Last time we talked about how to visually do it, and know that you could also use one of your tech tools like Help Plot 3D, plot a surface if it's given in an algebraic representation, rotate that view, and when you're looking for local extrema, you're just saying who is the tallest of nearby neighbors and who is the smallest. If you're also looking for saddle points, again, you're looking for those places that have like a min in one direction and a max in the other, places that you could actually straddle them. And then if you're looking for the global, we'll get to that in the next video. So you can visually identify them. In the first couple pages of this chapter 3 and journal 3, have you go through a few activities. And that visual is going to help you confirm some of your algebraic work. And so we're going to jump to the algebraic now, and there's several examples in your book, and then you're going to work some for your homework. And so I'm going to pick one that's not in the book, and we'll work that one. And so we want to, in this case, find the global extrema for this R3 function. Z is a function of x and y. It's given algebraically by this representation, x to the 4th minus 4x cubed plus 4x squared minus y squared. And the goal is to find the local extrema and saddle points for this guy. Okay, and so one of the things we know that extends from R2 over here in R3. What were good places to look for local extrema in R2? Those are places where we had horizontal tangent lines. And now we're just going to extend that to horizontal tangent planes, right? So we have the surface. So this was f prime of x equals 0 was the CP. We have the definition over here of a CP where both first partials are 0. So we're going to get both first partials. Those will be our horizontal tangent planes. Those are our CPs. Those are good places to look for local extrema. And then just like over here, just because you have a CP doesn't mean it was a min or max. You have to do a little more work. And over here, we had something called the first derivative test and the second derivative test. And those are ways to take this extra information and determine, is this CP actually a max or min? It's a good place to look. Might be a max, might be min, might be neither. Same thing's going to happen over here. We're going to use something called the D-test to figure out which of our local extrema actually are max or min, saddle points, or neither. Okay, so again, first derivative test and second derivative test, just to review those, make sure you got them. And we're going to extend that to something called the D-test. So we'll get to the D-test in a bit. For now, let's make sure we can take our critical points. It's a place where both first partials equal 0. So let's get the first partials and we'll set them to 0. By definition, these are forcing the slopes of a tangent line restricted in a y equals plane to be 0. So I have to have a horizontal line. And then restricting this one in a perpendicular direction to be also 0. So when those two happen, you actually have a horizontal plane. All right, so f sub x, easy because this is what is called separable. There are no interaction terms. All the x's are together, all the y's, and they're also nice polynomials, really easy one to take derivatives of. So 4x cubed minus 12x squared plus 8x and minus 2y. We have a system of equations. Two equations, two unknowns. They're nonlinear equations, but oftentimes these are easy to separate and solve. Second one, really easy, y is 0. Is that a CP? No, because remember CPs in R3 need both an x and a y component. So I got to do a little more work. I know all my CPs will have the second component, the y component, 0, but I need to get a little more information about my x components. So turns out this one, even though it's a cubic equation, it's going to be pretty easy to solve because we can factor out some stuff. So I'll make a little more space. Or actually, I'll fit it here. I'm going to take out a 4 and an x, because that might make the arithmetic a little bit easier. Minus, what is that, 3x plus 2 equals 0. And then that second factor is actually quadratic, so I'll try factoring a little bit more, see if they're even easier linear factors of this. So x and what, 2 and 1 are the only choices, minus, minus, it works out. Great. Okay, so I see the first equation gives me x equals 0, x equals 1, x equals 2. Those alone are not CPs, only if they're partnered with a y. So it turns out in R3 that we have 3 CPs. We have a CP at 0, 0, x, y, right? A CP at, what's the next one? 1, 0, and a CP at 2, 0. So this problem has 3 CPs. It'd be a good thing to stop the video now. Go to one of your tech tools. I saw a lot of you like Grapher, Wolfram Alpha, or there's CalPlot3D. Put in our function, zoom, pivot all around, rotate, until you verify that these actually are 3 critical points, places where you have horizontal tangent planes, which means there are good places where that horizontal tangent plane is actually forming a min, could be a max, could be a saddle point, I can't make my hands do that, or it could be neither. So that's the next step, we have to figure that out. And this is the part that's new. So this was all review from chapter 2, finding CPs. And now we're gonna do, the new part is the d-test. So I have to teach you what the d-test is. So I have to give you a definition. So let's move our CPs over here. We have 3 of them. 0, 0, 1, 0, and 2, 0. And then let's make room for D. So the definition of D is we're going to form this function. D is a function of x and y, and it's going to be our pure second partials, f sub x, x, f sub y, y, minus our mixed partial, f sub x, y, at some point x, y, squared. And I could square that because remember, for all the textbook functions we'll be working on, all the nice, well-behaved functions, f sub x, y equals f sub y, x. So that's why I can just put one of them and square it. And now I've actually covered all of my second partials in this definition. And D is a thing that we're going to compute and evaluate. And we're going to evaluate it. This is in a box in the beginning of the chapter. This page here, finding local extrema. What are we, 232? So this little box down here is the one that you're going to want to know to work these problems. There are cases. We're going to evaluate this D and decide, is it negative? If it is, then it's a saddle point. Is it positive? Well, then I need to check additional condition. If f sub xx is also positive, then we'd have a local max. All right, so we're going to continue and check these. And then something else can happen. If D is 0, the test fails. And that actually happens over here as well in your second derivative test. If D equals 0, the test was inconclusive. Go back to the first derivative test. So that could happen to us as well here. All right, so let's go ahead and evaluate the D, and then we'll go to our box and check which of the cases we're in. And then we'll see that it's actually, you don't have to memorize the cases. They actually make a lot of sense, common sense, and they fit in with R2 stuff. All right, so you're going to form this D, and you're going to evaluate it at each of your critical points. So we have 3 critical points, so we have to evaluate this D at 3 things. So we're going to form D at 0, 0. This is for the critical point 0, 0. We're wondering, is this critical point a max, a local min, a saddle point, or neither? And so we're going to figure out what its D is. To do that, notice we need a little more work though. We need f sub x, x, f sub y, y, f sub x, y. So let's see if we can squeeze them in here. F sub y, y is easy. At any x, y, no matter what it is, you're still just going to get minus 2. F sub x, x, also easy. A little more work to write it though, it takes a little more time. Where's that? 12x squared minus 24x plus 8. And we need one more partial, f sub xy or f sub yx, they're the same thing. It might be easier down here. F sub yx is 0. F sub xy is 0. So I'll stick that over here. F sub xy is 0. And that's for any xy, right? I guess I'm being sloppy on that, but I should write it. And any xy is 0. So it doesn't matter what xy you gave me, it's always going to spit out 0. Same thing here, it doesn't matter for yy. Whatever xy you give me, it's just going to spit out minus 2. On the other hand, f sub xy does depend on what x you give it. you have to plug it in and get a number. Okay, so let's go ahead and do d sub 0, 0. So I need f sub x, x at 0, 0. So I'm just going to write it all out, this time in detail. Once you've done one or two of these, you'll have some shorthands. All right, then we start evaluating for our particular function. What is f sub x, x of 0, 0? So I come back into my f sub x, x, plug in 0 for x, 0 for y, and I'll have 0 minus 0 plus 8 is 8. Times f sub y of 0, 0. So I go to f sub y, plug in 0 for x, 0 for y, and I still just get minus 2. And then f sub xy at 0, 0. I plug in 0 for x, 0 for y, and I get 0. And then I square it, minus 0 squared. So this is going to be minus 16. So this d at 0, 0 evaluates to minus 16. That's probably going to be different than what happens when we evaluate d at 1, 0, right? That's the other CP we're interested in. Is the CP at 1, 0, 0 max, min, or neither, or saddle point? We'll have to get its d and figure it out. But we finished the d for 0, 0, so we can go ahead and do our interpretation. And from our box on page 232, here we go, our box at the bottom here. We are in case 1 then. If d is less than 0, your CP is a saddle point. So anytime you get a negative d, you have a saddle point. So our conclusion is that the point 0, 0 is a saddle point. Again, be a good time to pause the video, go to the tech tool, plug this function into Calcplot 3D, check not only is it a horizontal tangent plane there, but it's also a saddle point. Looks like a max in one direction and a min in the perpendicular direction. All right, let's do 1, 0 for this one. We have to finish for each CP, we have to do this. So we have a little more room on the board before we need to erase. So d of 1, 0 is going to be f sub x, x at 1, 0, f sub y at 1, 0, minus f sub xy at 1, 0, all squared. Okay, your x, x, y, y minus xy, you plug in for your particular point, x, x at 1, 0. So I go back to second partial, plug in 1 for x, 0 for y. So 1 for x is going to be 12 minus 24 plus 8, which is what, minus 4? All right. And then f sub y at 1, 0 is still just minus 2. Minus f sub xy at 1, 0 is still 0, squared is 0. So we'll have positive number. Now, positive number means if it was negative, you're done, you know it's a saddle point. If it's positive, you're in either case 2 or case 3, and you have to check one more condition. So case 2 and case 3, the additional condition that you're going to check is the x partial. So that's sitting right here. So I'm now asking myself, is that x partial negative or positive? In this case, it's negative. And because it was a second partial, it has to do with concavity. So let's review from back over here, right? If your second derivative was negative over here, what's the conclusion? Well, that tells you that your CP was at a place where it was concave down, so therefore you are max. Same thing happens here. We only have to measure that concavity in one of the directions. We only have to check XX with this test. And when we do check that, we get a negative, and that tells us that we're actually concave down in that direction. And therefore, because we're concave down, instead of just being a 2D curve, it's now a surface that's bent, but it has this bend. This concavity down makes it a local max. So d was greater than 0, and f sub xx was less than 0. And so that is when you're in case 3. Or again, don't remember cases, just remember that it's concave down, makes it a local max. At 2, oh sorry, that was 1, at 1, 0. All right, that's just in the x, y, but if you wanted to get the z component, how would you do that? So again, some books, some textbooks will ask you, where is that in a 3D point on the surface, right? So we know the x and the y. If you get the z, you always go back to the original function. You plug in 1 for x, 0 for y. So let's see what we get. 1 minus 4 plus 4, so 1. So at that point on the surface, we know we have a local max. All right, so where are we at? We checked 2 of our CPs with the d-test. We determined the first one, 0, 0, was a saddle point because the d was negative. The second one, we determined was a local max because d was positive and f sub x was negative, made it a local max. Case 3. One more to check. Let's quickly go through that one. Make some space here. So we want to check the last CP is at 2, 0. So I just need to change these things right here to 2's. And we'll see part of this stays the same, f sub y, f sub x, y. Those ended up being constants for this particular problem. So 0 squared minus 2. And now we need f sub x at 2, 0. So that's the last piece of the puzzle. So we're going to plug in 2 for x, 0 for y. There is no y, so I just had to plug in 2 for x. So it's going to be 2 squared is 4, 48. Maybe not do this one in my head. I'm not good with my quick arithmetic. Minus 48 plus 8. Can you do that right? 2, 0. Yeah. Okay, so that gives us 8 times negative 2 is negative 16 minus 0. So d is negative. Therefore, you have a saddle point at the point 2, 0. And if you wanted the corresponding z value, you would go back and plug into the original. That's a little bit more computation than we need to do, so you get the number there. All right, so you could check all 3 critical points on a tech tool, are horizontal tangent planes, and they each satisfy what was our conclusion. Saddle point here, local max. So visually verify that. Take a moment, pause the video, and check that out. Also, again, one last thing, the d-test, this box that you're going to be learning from. If you're a person that likes to just put that in your study guide and memorize, you can, but hopefully you also just see that it makes sense and you don't have to think about cases because you can just think back to things you remember over here from Calc 1 and R2. All right, let me see if there's any other comments on this section. Oh, one more, okay. D-test. The last case, case 4, the d-test can fail. If d is 0, what happens? That does happen sometimes, not too much in textbook problems, but I'll give you an example of one just to quickly show you it is possible. And what does that mean? Usually it's not a big deal because often when it's happening, the surface actually was simple enough that we could evaluate otherwise. So here's an example of a surface z equals x squared. And so we get to review a few things here. Z equals x squared. What does this thing look like? Pause the video and see if you can draw it for a moment. All right, you come back from that. Z equals x squared has one free variable, right? So y is free. And sometimes write that as an explanation, right? It makes it a little bit easier. Or in the easier case, in the zx plane, this is a parabola opening up from the origin. Then when you add the y-axis coming out from the board, this extends. So in R3, this is a half pipe extending along the y-axis. So I'm going to draw my skewed parabola here in the skewed CX back wall, and then draw another copy of here, try to replicate the same angles, connect the ends, and there's my half pipe. R3 surface with one free variable. Okay, so where are the local extrema? You can, again, check with a tech tool, or we have this visualization here, or you pulled out a piece of paper and visualized in your desktop coordinate system. And pretty easy to see, right, that their local extrema turn out to be global extrema. We'll figure out how to check that later. For now, we know that local extrema, or anywhere along this sort of bottom spine, right? And it'll turn out that there are no global extrema because this will extend infinitely upwards. And that's okay. We'll be able to find global extrema over some restricted finite domain if we were interested in that. So let's just see what happens to the d-test though. So we visually see, yeah, everything along this line, which turns out to be the y-axis, is a local min that turns out to also be a global min. So we visually know that, but let's just see what happens with the d-test if we were to do this. So the d-test needs partials, so let's get the first partials, and then we'll get the second partial. The only way to get the second partials is through the first partial, so we gotta do a little prep work. So f sub x, f sub y, f sub x, x, f sub x, y, and f sub y, y. That's a horrible y. A little bit better. Okay, so we have all the information sitting here that we need for our d. Let's form the general d for any x, y, and then we'll see what happens with that. Oh, by the way, what are the critical points? So we see right here there's nothing to really solve for, and then right here x equals 0. So a critical point in this example is anything, sorry, anything with x equal to 0, any y value. And notice that that actually is the definition of the y-axis, right? X is 0, and any y value makes the y-axis. So we actually have infinitely many critical points, and they are all along the y-axis. And then we're trying to see, does the d-test tell us that those are min? We know the critical points. We know the horizontal tangent planes, which are good places to look for possible extrema. Does the d-test help us? And so d at any xy is, by definition, f sub x, x at xy, f sub y, y at xy, minus f sub xy at xy squared, which is, in this case, f sub xx is, for any xy, is 2, f sub y, yy for any xy is 0, it turns out it's a constant, minus xy, 0 squared, so 0. So the d-test, this is an example of case 4. The d-test didn't help us. It's inconclusive. The d-test fails to tell us whether these CPs, the y-axis or local min or local max saddle point or neither. And in this case, it's such an easy surface that it doesn't really matter that the d-test failed. We have other means to figure out local extrema for this problem. But just know it could happen, it could exist. All right, that's it for this one.